Okay, in the previous lecture, I just tried to give you some sort of overview of deep learning and some success stories of deep learning. And I told you that the building block of neural network is perceptron. The most straightforward structure of neural network is feed-forward neural network. And feed-forward neural network is basically collection of some perceptrons. Each of these circles is a perceptron. This is a shallow network, a simple feed-forward neural network. We call this one input layer. So suppose that you have d-dimensional input. So your input is a vector in Rd. In this case, it's in R4. So I have 4 measurements about an object. And you feed it to the network. So this is your input. And these are perceptrons. And then you have output. So this is called output layer. This is called hidden layer. And this is called input layer. If you have many hidden layers, then you have a deep network. So it's not quite clear that where the threshold is. More than 2 layers is deep. More than 3 layers is deep. In fact, some of these success story that you have heard about deep learning or some of the algorithms that are successful in the area of deep network are not really that deep. They're shallow networks, but they're claimed to be, a successful algorithm for area of deep network. For example, word2vec, which I mentioned the other day, is quite popular algorithm in natural language processing. It's used, but the network is not a deep network. It's shallow network with 1 layer. But anyway, when you have many hidden layers, it's deep network. And as I mentioned the other day, the main issue and the main problem was that we didn't know how to train networks when there are many layers of hidden units. And then this is something that recently we learned, actually. We know how to do it. Okay. So today, actually, I'm going to start with perceptron and then backpropagation. I know many of you may know perceptron or backpropagation, but the promise is that this course is supposed to be self-content. So even if you know perceptron, bear with me for half an hour, and then we go through that. But I think it's important to basically understand the building block of a neural network quite well. So a perceptron okay. A perceptron is basically a simple unit which has 2 parts. The first part of a perceptron simply compute a weighted sum of inputs. So suppose that you have a d-dimensional vector. And this d-dimensional vector is the input. Basically, you have d features or d variables for an object. And this is the input of your perceptron. What's happening in this part of perceptron is to compute a weighted sum of these d measurements. So basically here, it's going to be some beta 1 times x1 plus beta 2 x2 beta d xd. So here I basically have this summation, beta I x I for I equal 1 to d. Sometimes I add scalar to this, beta null. So in vector form, if beta is a d-dimensional vector, what's happening here is beta transpose times x, when x is a vector and beta is a vector. Okay? So the first part of perceptron, this part of perceptron, would be simply a weighted sum of inputs plus a beta null. The second part of the perceptron is a nonlinear function, which is usually called activation function. When we apply a nonlinear function to this weighted sum, traditionally, this activation function is a step function. So if beta transpose x plus beta null is negative, when you apply a step function to it, the output would be -1. And if it's positive, the output would be positive, +1. Okay? So the output of the perceptron is either -1 or +1. And traditionally, it has been used to classify two classes. Suppose that the label of one class is -1, the label of the other class is +1. And then you want to set these weights, beta 1 to beta d, and beta null. These are parameters of your model. You want to set them in a way that the output basically predicts the label of the class. So if you choose one object from class 1, the output is 1. If you choose an object from class -1, the output is -1. So we want to predict the label correctly. Okay? So to find beta and beta null, as I told you, when it was invented in 1958, they didn't know how to train the weight, how to train the perceptron, and they used to randomly change the weights until it works for some problem. Later on, we learned how to train, okay? And by training, I mean how to find beta and beta null. To find beta and beta null, we need a cost function. We need an objective function. In general, in any machine learning algorithm, there are 3 steps. The first step is that you want to model your data using a function f. And this function f, you're assuming that it comes from a hypothesis class. You have to make some sort of assumption that which hypothesis class can model this data. So I assume, for example, that a linear function can model my problem. So my hypothesis class is class of all possible linear functions. Okay? I may assume that a quadratic function, a polynomial function in general, is going to model my problem. So first I assume that there is a hypothesis class and my function comes from this hypothesis class. Okay? And we always have this step. No assumption, no learning. This is famous no free lunch theorem in machine learning. Okay, no free lunch theorem basically says if you don't make any assumption, you can't learn anything. You have to make some assumption. Okay, so we assume something about data. We assume that a function comes from hypothesis class. And the second step is that, okay, in this hypothesis class, there are many members. Which one I'm gonna choose, the set of linear functions. Which linear function is going to fit my data the best? So how I'm going to evaluate, if you choose one member of this hypothesis class, how I'm going to evaluate this member? Is it good? Is it bad? So I need to basically score them. And this scoring is what's called a cost function or objective function. And then we need to find, I have a scoring function. So basically, I can, among all elements of this hypothesis class, I can score them. I have to choose one among all. And there's a search strategy to choose one. And this search strategy is optimization. You form it as a convex optimization problem. You can make it convex. It's non-convex. You use gradient descent, stochastic gradient descent, conjugate gradient, Newton method, You have a search strategy to find that one. So in this case, our hypothesis class is class of linear functions. So we are assuming that there are two classes to be classified. So positive labels of one of them, and negative is label of the other one. And I assume that a linear function is going to classify them. So this is my hypothesis class, function of linears. And there are many of them. Then I need a scoring function to score them. Which one is better among this linear function? Which one is better? And then I need a search strategy to find one. So the fact that it's linear, I told you, it was not clear in 1958. It took many years for researchers to realize that it's just a linear discriminant function. But we know it now, that perceptron is just a linear function. We need a cost function, and you can have many different cost functions. You can score them in many different ways. And based on the way that you're scoring them, you get many different algorithms, So again, traditionally, the way to score them is to find the distance of all misclassified points. So basically, among all possible lines that can make distinction between these two classes, I'm looking for the one which misclassifying points less. Not only misclassifying points less, but the distance of the discrimination function or the hyperplane is smaller compared to other possible cases. The score of this one compared to the score of, say, for example, this one. In this case, no point has been misclassified. So the summation of points that have been misclassified in this case is 0. In this case, there are points that have been misclassified. This point is misclassified, and this point is misclassified. So I'm assuming that everything on one side of the hyperplane is negative, on the other side is positive. But it turned out that these 2 points are on the left side, supposed to be negative, but really they are positive. So they have been misclassified. So the distance of these points to the hyperplane, the summation of these two distances, is my cost. So I have to minimize this. I don't like this. I'm looking for the hyperplane which has minimum distance of misclassified point to my hyperplane. So we decide to choose this objective function. You can decide to have many other objective functions here. It could be just the number of points that have been misclassified. It could be cross entropy, for example, which we haven't learned about yet, or likelihood, something else, But we choose to have this cost function. Okay. Now what I have to do is to write this cost function in a mathematical way. Okay. So I have to basically distance of all misclassified point, write it in a mathematical way. Okay, how to... we know that the perceptron is just a linear discriminant function, and any linear function can be expressed in this form. Okay, let me tell you a little bit about geometry of this hyperplane, learn a little bit about the property of this. If I choose 2 points, x1 and x2, on this hyperplane, then both of them are on the hyperplane, so they satisfy this equation, beta transpose x plus beta null equal to 0. This is the set of points that satisfy this equation. So the first thing that I can say about this is that beta transpose x1 plus beta null is equal to beta transpose x2 plus beta null. And it's equal to 0. Because both of them are on the hyperplane. So it means that beta transpose x1 minus beta transpose x2 is equal to 0. And it means that beta transpose x1 minus x2 is equal to 0. So x1 minus x2 is a vector. Okay? So this is a vector. And beta also is a vector. And now I tell you that the dot product of two vectors is equal to 0. So what do you conclude out of this? The dot product of two vectors. It means that these two vectors are orthogonal, right? It means that beta is orthogonal to x1 minus x2. So it means that if you have the equation of hyperplane, that beta is orthogonal to the hyperplane. That's first property. Second, for any point here, for any point x null, we know that beta transpose x null plus beta null is equal to 0. It means that for any point, beta null is equal to negative beta transpose x null. Right? Okay, now suppose that I give you a point here, x, and I want to compute the distance between this point and the hyperplane. Don't forget that our cost function is the distance of all misclassified points. So first, I need a way to find the distance of points to the hyperplane. So I have a point x, and I would like to know the distance of this point to the hyperplane. I would like to compute this distance. Any suggestion based on the properties that we learned? Yes?
Euclidean norm? Like the norm between two vectors?
Which two vectors?
x2 and x, which is the one we talked about?
This is x.
Yeah. And compute the norm between that and x2 minus x1.
Okay, and how does this help?
Well, we know the distance then between the two of them.
So that would be basically Euclidean norm between x and this vector.
Yes.
But I need this.
Okay.
Yes.
You can find the projection of the point on the hyperplane by moving along the direction beta.
Okay.
And then once we have the projection, we can compute the distance between those 2 points.
Right. Yes, exactly. I need to project this on this direction, on the direction of beta. So this point, let me erase these things. I call this point x null. Okay. It's trivial to find this distance, x and x null. I can just subtract x minus x null. But to have the distance, I have to project it in this direction. And that would be my distance. Okay? So basically, to find this distance, I can simply compute x minus x null and then project it in the direction of beta. Project this in the direction of beta means compute beta transpose times x minus x null. Okay? Does it make sense? Okay. So beta transpose x minus beta transpose x null minus beta transpose x null is beta null. So beta transpose x, negative beta transpose x null is beta null plus beta null. So beta transpose x plus beta null is this distance. That's what we are looking for. Give me an x, and the question is that what's the distance of this given point to the hyperplane? So the only thing that you need to do is to put this in the equation of the hyperplane. Okay? But we are not quite done, actually. You know, if the point is on the hyperplane, beta transpose x plus beta null is equal to 0. If point is not on the hyperplane, if I'm on one side of the hyperplane, then this is going to be positive. I'm on the other side, this is going to be negative. If I'm the same distance from the hyperplane here, and compute this projection, this is going to be negative, and this side is going to be positive. When I'm talking about distance, distance is always positive, right? I don't care that the point that has been misclassified is misclassified on this side of the hyperplane and on the other side of the hyperplane. I don't want any point to be misclassified, okay? So I'm looking at the distance, not sign distance. So the distance, you know, this could be positive, this could be negative based on the sign. I want it to be positive all the time. What should I do?
Class label.
Sorry?
Class label.
Class label what?
Multiply this one to class label.
I can multiply this to class label. Okay? So if I'm on this side, everything's supposed to be positive, so multiply to positive number is positive. I'm on this side, everything is negative, multiply to class label, become positive, right? I can also take absolute value. Why don't we take absolute value simply?
It's not differentiable?
It's not differentiable, you know. I mean, for cost function, it's important to be differentiable. Non-differentiable cost function doesn't help us in search. So always we need a cost function which is differentiable. So I can take absolute value simply, but I don't do that because then it's not differentiable. But I can multiply this by class label. So basically, my d distance would be class label for point I, would be class label times beta transpose xi plus beta null. So that's my distance of point xi to the hyperplane. Yes?
Transpose has to be unique vector.
Sorry?
Beta transpose has to be unique vector.
Beta transpose needs to be unique.
Unit vector.
Yeah, that's a good point, actually. You know, beta needs to be unit vector, you know. I mean, if you want this calculation to be precise, when we are talking about distance here, you have to make sure that beta is normalized, means that this beta should be divided by the norm of beta. You know, everything needs to be normalized. You have to divide by. But I simply assume that these betas are normalized. You know, you can, whatever the beta is, beta transpose, divide by the norm of beta, I call it beta. You know, I assume that these betas are normalized. But you're right, it's supposed to be normalized. Okay, this is the distance of a point to the hyperplane. So remember what was our cost function? Summation of all distances of misclassified points. Points that have been misclassified. Points that are misclassified are on the wrong side. Right? So the sign needs to be flipped. You know, the positive label is on the negative sign. The negative label is on the positive sign. So for misclassified point, actually the distance is negative yi beta transpose x. And then my cost function, which is a function of beta and beta null, is simply the summation of this minus yi beta transpose xi plus beta null. Is that clear? Okay. So we have a hypothesis class of linear functions. We have a scoring. So I'm going to score them based on the distance, the summation of distances of misclassified points. Now I have to minimize this. I have to minimize this cost function because I'm looking for the line. I'm looking for discrimination function which has the minimum distance to misclassified points. So if I classify everything correctly, this is 0, for example. And if I classify them in a wrong way, then I have to pay some cost. Yes?
So the solution is over all points or just
Over all points that have been misclassified on set M. And M is a set of points that have been misclassified. Not all points, only misclassified. Okay. So I need to minimize it. Basically, I need to find beta and beta null in a way that this is minimum. How can I do that?
Use derivative.
Sorry?
Use derivative.
Take derivative, right? So I have to take derivative of this function with respect to beta. And I need to take derivative of this function with respect to beta null. What is the derivative with respect to beta? Sorry? Negative yi xi. And what's the derivative with respect to beta null? Just negative yi. Right? So I have derivative. So now I have the derivative, so what's beta now? What's beta now? There are many different search strategy. There's many ways to optimize the cost function. Sometimes you have closed form, sometimes you have to use numerical method. A method that is common in neural network is gradient descent. And gradient descent basically means that you have a cost function and you need to take to this point. Gradient descent means that I'm at this point. I take the gradient. Gradient is tangent to the surface, right? So that's gradient. That's tangent. Basically, it tells me the direction toward the minimum. And then I will take one step toward the minimum. Then compute the gradient again. And gradient will tell me the direction again. And then toward the direction, I will take another step. It's a very simple algorithm. It's called gradient descent, right? So at each point, I will take one step. And then I take the gradient again. And I take the gradient again and again until I get here. In fact, in gradient descent algorithm, there is no guarantee that I get here. It's possible that this is just a local mean. So I get here, and then I take the gradient, and the gradient tells me that's a good point, stay here. You don't need to go anywhere. But that's wrong. I need to go here. That was a problem for backpropagation that we are going to learn, and in gradient descent in general. That was a problem for neural network. That neural network doesn't have a convex cost function, it's non-convex, and it's quite possible that you get stuck in local mean. That was one of the main complaints about neural network. But you don't hear this complaint anymore. The reason is not that gradient doesn't get stuck in local mean. The reason is that when you are in high dimensional space, there are many local means that are as good as each other. Means really it doesn't matter if you get stuck in local mean in high dimensional space. And now we are working with very high dimensional space, so we don't see the effect of local mean as we used to see in the past 20 years ago. 20 years ago, your data was two-dimensional, three-dimensional, and when you optimize, there was a great chance that you get stuck in local mean, and there was a great chance that this local mean is really bad local mean. Okay, but there are mathematical reasons behind that, but intuitively, you can appreciate the fact that, when you have a local mean like this in two-dimensional space, it's quite possible that you get stuck here. But just imagine that this surface is three-dimensional. If it's three-dimensional, there is some chance that you can escape from the third dimension. Even when you're stuck in this two dimension, there's a chance that you get stuck. You can escape from the third dimension. Okay, and with like modern data that the dimension is hundreds, sometimes millions, right? There are quite a high chance that there is some way to, escape from the local mean and eventually get to a point that, so that's the reason that you don't hear more or you don't hear often about the problem that used to be a very serious problem for neural network 20 years ago. But you don't hear this anymore because we're working with high dimensional data. Not because we have a better search strategy. Yes.
But doesn't your training stop the moment you converge at a local minimum?
Sorry?
Doesn't your training stop the moment you converge at a local minimum? Even if you have many chances to escape, if you converge at a local minimum?
Yeah, you converge to local minimum, yes. I mean, there is no guarantee that you converge to global mean. You converge to local mean. But the point is that in high dimensional space, there are many good local means. Many. So you converge to local mean, but it's a good one. It's not a disaster, usually. Could be a disaster, but usually it's not. Okay? So gradient descent actually, as I said, it's just, a procedure that when you want to find beta, your new beta is the old beta minus a small step toward the gradient. So you take gradient, it's basically direction towards the minimum, and then you take one small step. This is called learning rate. And learning rate tells you how large or how small your step should be. Large lambda means you take a large step, and a small lambda means that your step is small. Should we go for large or small?
Somewhere in between.
Why?
Because if it's too big, then you might step over the local mean.
Okay.
You can just pass the global minimum.
If it's too large, it's possible that I'm here, and I want to take one step, but this type of one step means that I will jump here. And then I take a big step again, and then I will jump here. I never see this point. And if it's too small, the learning will be quite slow, because I take very small steps. So in fact, in practice, the learning rate would be adaptive. So we start with the large, and then we make it small when we are closer to the point. Okay. So these are the properties that I told you. And as you mentioned, this vector needs to be normalized. But I just assumed that it's already normalized. And then you have this cost function, and then gradient descent basically would be a procedure of this form. And for this case, actually, since the gradient the derivative with respect to beta is this quantity, and derivative with respect to beta null is this quantity, your algorithm have this form. Okay? You can update your beta and beta all until it converges. That's traditional way of doing perceptron. Okay? So you can change this cost function to another cost function, and then it's going to be identical to logistic regression, for example. Okay, there are some properties about perceptron. One is that if data is linearly separable, theoretically, it's guaranteed that the algorithm will converge to a separating hyperplane. If data is linearly separable, sometimes data is not linearly separable. There is no line. If there is a line, then it will converge. But the number of times, the number of iterations, the number of times that you need to go through this until it converges depends on the gap between two sets. So I said they're linearly separable. Linearly separable means that for beta transpose x plus beta null, there is always a constant, okay, such that this is greater than equal that constant. So there is always some distance to the hyperplane. This means that it's linearly separable, and this is the gap. If this is a small, it's hard to converge. So two data sets are close to each other. There's a small gap, hard to converge. They're well separated, easy to converge. Okay, so the solution is not unique because it's not convex. It's going to get to a minima. So it depends on the initial value, you're going to get a stuck somewhere. Okay. And so a perceptron can only discriminate between two classes. That was something that it's trivial now, but it was not trivial. As I told you, for many years, people thought that they solved AI with perceptron, and then they realized that no, it's just a linear discriminant function, and people were surprised that they can solve XOR problem using perceptron. So they were surprised that, okay, it's linear. They can do that. Okay, I told you about the small gaps, so these are not important. You can see them later, and this is the definition of gap between and definition of linearly separable, and the convergence rate depends on this constant. So I skipped them. So let's, if there's no question about perceptron, let's get to neural network now, which is basically, collection of these perceptrons. Any question? Okay. So neural network and feed-forward neural network, as I told you, is layers of perceptron. Okay? So instead of one perceptron, I have one layer of perceptron and another layer of perceptron. And so for one perceptron, I had this input and one output, which could be 0 or 1. Now assume that you have inputs here, x1 to xd, and then instead of one perceptron, you have many of them. And, this goes to everywhere. And then they have some output, but this output goes to another layer of perceptrons. So this goes here, this goes here, this goes here, and so on. So basically, each perceptron is linear sum of the input and then a nonlinear function. And you apply this many times. So it's a composition function, right? F of something, which each layer is one of those f's, one of those sub-functions of a very complicated function. So people started actually to combine these perceptrons and solve more complicated problems like XOR problem, for example, but they didn't know how to train it. And it was not as easy as perceptron to train. One algorithm which was a real breakthrough in the area of neural network and made neural network become famous was backpropagation. And actually, backpropagation was a way to compute the derivative of the cost function with respect to one of the parameters, which is the weight, right? So in the case of perceptron, it was easy, it was trivial to compute it was easy to compute the error with respect to weight, W1, WD. That was my weight. It was easy to compute the derivative of error function with respect to this beta. Now I have many of these perceptrons in different layers. I have many of these layers. And the cost function here, this is my output y hat. And there's a true y. And with some cost function, I want to minimize the distance between what I predict and what it's supposed to be. But I need to take derivative of this cost function with respect to this weight, for example, with respect to this weight. But it's a very complicated function, As I told you, it's f of. It's many nonlinear function has been applied to get to this point, and it's not trivial to compute the derivative. And backpropagation was a way to compute the derivative. Okay? And now we want to learn about backpropagation. This is just a snapshot of a neural network. So I have, say, for example, layer L, layer I, and layer J. In each of these layers, there are many perceptrons. Okay? And somewhere here, I have the output, and somewhere here, I have the input. So I have many layers. I have chosen only 3 layers and 3 perceptrons of these 3 layers. In each layer, 1 perceptron. So I told you that each perceptron has 2 parts. The first part is just a linear sum of the input. And the second part is a nonlinear function applied to this weighted sum, right? So this part A, is just a linear sum of the input. So A is sigma of ZIUIL. This is UIL. This is one of the weights of the input. This weights times whatever was the output of the previous layer. When I take the summation of this over all inputs, that would be the value of AI. Okay? Then in the second part, I apply a nonlinear function to this AI. In the traditional and conventional way of doing perceptron, this nonlinear function was a step function. Step function is not differentiable. And that was one of the reasons that we had a hard time, to change our cost function, the summation of distance. Yes?
Now they use values, and those, by the same principle, those aren't differentiable. But
Yeah.
they're subgroups, right?
Yes. Yeah.
So differentiability doesn't, like in this case, it's on each interval.
In each interval, yeah, you're right. But I will mention this in a minute, that, what's the role of this. So this nonlinear function which we apply to A could be any nonlinear function. And there are some popular nonlinear function. One of them has this form, a logistic function. Another one has exactly the same form, but the difference is that this is between -1 and +1. You could have the same form between 0 and 1. So logistic function or tangent hyperbolic function. And recently there is a function which is called ReLU, rectified linear unit, which has this function, which I get to this in a minute. For the moment, forget about this one. So there's a nonlinear function applied to A. And this nonlinear function, for example, could be a logistic function. It could be other functions. Okay? So this is in terms of notation. And this network, has some layers. At the end, it produces, yes?
Just a question about the notation.
Mm-hmm.
So what is the UI I?
This is UIL. And this is ZL. This is ZL times UIL becomes AI.
And that is summed over all.
Sum over all of these ZLs. You have many perceptrons on the layer L. Each of them have an output. I call the output of perceptrons of this layer ZL. Over all of them, multiply by the corresponding weight, sum, it will be AI. Right? Okay, so there are many layers here. It's somewhere here I predict y hat. Okay? And then I want this y hat to be close to y. Let's go for the simplest cost function. And my cost function is y minus y hat squared. Okay, so I want y to be close to y hat. But my job is to take derivative of this cost function with respect to one of these weights, one of these parameters. Derivative of y minus y hat with respect to UIL. Any suggestion how we can take this derivative? Yes. But in fact, backpropagation is basically chain rule. You apply chain rule multiple times, and the chain rule and recursion. Okay. So it's not quite clear how can I take this derivative with respect to UIL, but I can apply chain rule and write it as derivative of y minus y hat with respect to AI. And then derivative of AI with respect to UIL. Okay. Now, how does this chain rule help? So what is derivative of AI with respect to UIL? AI with respect to UIL. Sorry?
Again, we can split it.
Remember, we have layer L. We have layer L, we have layer I, and we have layer J. And AI is simply summation of all of these Z's times corresponding weight. So basically AI is this Z times corresponding weight plus this Z times corresponding weight plus this Z times corresponding weight. And now I'm taking derivative of AI with respect to one of these weights. So what would be the derivative? The corresponding Z, right? So derivative of AI with respect to UIL simply would be ZL, the corresponding Z, right? So I know this derivative. But what's the derivative of this cost function with respect to AI? This is hard, actually. I don't know what that is. So I call this the hard part delta I. I don't know what the delta I is. But this part I know. It's ZL. So the derivative of cost function with respect to UIL would be delta I, which I don't know what delta I is, times ZL, which I know. Now I have problem with this delta I, so I have to compute this delta I somehow. So delta I is derivative of y, derivative of the cost function with respect to AI, which was hard to compute. Okay. Now, any suggestion now how to approach this? Yes.
Use chain rule again
Use chain rule again for
on ZI.
on ZI. Okay. So I have derivative of y minus y hat with respect to AI. So you suggest that I write it as derivative with respect to ZI.
And then di ZI by di AI.
Okay. So how does this help?
You can
Sorry?
you can continue in that manner until you get to your output layer.
No, if I do I know that what's the derivative of this with respect to ZI? I mean, I have another quantity which is unknown. And do I know the derivative of ZI with respect to AI? This I know. I mean, this is easy, but this I don't know. So I had a quantity, which I called it delta I, which is unknown. But you can compute this unknown quantity based on another unknown quantity. And then I have to do something about this one. Right? But I have a better suggestion, actually. Actually, I don't have the better suggestion. Those who invented backpropagation had a better suggestion. So I want to take derivative with respect to AI. Why don't I take derivative with respect to AJ and then AJ with respect to AI? Why this is a better suggestion than your suggestion? Because derivative of this with respect to AJ is just delta J. It has the same nature as delta I, which was unknown. If I can handle this, it means that to take derivative of the cost function with AI of one layer, I can express it in terms of delta of another layer. In your suggestion, it was altogether a new quantity, which has nothing to do with, but it has the same quantity just for another layer. Okay? So is this chain rule correct? There's something missing here. Sorry? Summation. Summation over
All J.
here? Summation over all J's. Why should I have this summation?
Because AIs depend on all the AJ before.
Exactly. You know, what's the meaning of this derivative? It means that I perturb I, and I would like to know what's the effect of perturbing AI on this cost function, right? And the chain rule tell me, okay, you want to know what's the effect of perturbing AI on this? I will tell you that it's can be written as if you perturb AJ and then to see how AJ changed the cost function, and then you perturb AI and see how AI changed AJ. But so I have to perturb AJ to see what the effect of AJ is on AI. But there's many of them, you know. Any of these AJ, if I change, if I perturb, they're going to change this, right? So it's a summation over all of them, not only one. So so this is AI, and AI can be written as summation over J of this cost function over AJ, and then AJ with respect to AI. And this part is just simply delta J. So I was about to compute delta I. Now I can express delta I in terms of delta J. Okay. So this is delta J. But AJ with respect to AI, how can I approach this part, the second?
ZI, UJI, and we can use that derivative.
Yes. You know, I need derivative of AJ with respect to AI. I can write a chain rule again for this part. AJ with respect to ZI, and then ZI with respect to AI. Then I can compute both of them. You know, so I write AJ with respect to AI, AJ with respect to ZI, and then ZI with respect to AI. AJ with respect to ZI is what? Simply UJI. And what is ZI with respect to AI? Sorry? Compute the derivative of that nonlinear function, sigma, right? Sigma was a nonlinear function applied to AI and produced Z. So derivative of Z with respect to AI would be simply the derivative of that function, whatever that function is. Okay? So this is UJI. AJ with respect to ZI is UJI. And ZI with respect to AI is just the derivative of whatever nonlinear function I have chosen at point AI. So what's good about this is that I can express delta I in terms of delta J. So remember what we did at the beginning. You know, we wanted to compute the cost function with respect to UIL. And we realized that this is going to be delta I times ZL. ZL is known. Delta I is unknown. But delta I itself can be computed in terms of delta J. Delta J itself can be computed in terms of delta K, right? And I can go over and over and over up to get to the last layer. And I can show you that delta for the last layer is trivial to compute. Then you can come back, right? You can come back. It's a recursive function. You know, you need the derivative of this one. It depends on this one. This one depends on the next one. Get to the last layer. And last layer is trivial to compute. Then get back. Okay, then you can compute all of them. So, you know, this sigma, for example, is a sigmoid function. Then derivative have this form, usually has a closed form. And, you know, that was the formula that we had here. And note that this can be out, you can take this out of the summation because it has no index of J. You know, delta I is basically sigma prime AI, then sigma this quantity, and that's what we have here. You know, we can take this out of this summation. So, and this is the recursive definition of delta I. Yes?
Do you assume that sigma is differentiable from it?
Sorry?
Do you always assume that sigma is differentiable?
Yes. In ReLU that I mentioned, It's not differentiable, but I will get to that in a minute. But yeah, you assume that it's differentiable. Okay. Now, suppose that you have all of these layers, and you want to compute the delta for the next layer, the next layer, and the next layer. And suppose that the last layer is this one, k. At layer k, which is the last layer, what's going to happen? A perceptron has this part a and z, and delta is derivative of y minus y hat with respect to a. That's the definition of delta. Now I'm going to compute delta for the last layer. In the last layer, the output is y. Without loss of any generality, I'm going to assume that the last layer doesn't have z. It's just a. Why I say without losing any generality? Because, if this is your function, if this is your network, and your last layer has z, I'm just going to add a new layer to this, which doesn't have z. And whatever this z is goes here and goes out. Doesn't do anything to it. So just for simplicity, assume that the last layer doesn't have z. And then I have to take derivative of my cost function with respect to a. But what is a? A is really y, right? Because there is no nonlinearity. Something happened here, which I don't care, and you have a. I don't apply any nonlinear function to a, just the output would be whatever I computed, a. I call it y hat. So y hat is a. So in the last layer, when I take derivative of the cost function with respect to a, in fact, I'm taking derivative of cost function with respect to y hat, which is trivial to compute, right? It's just 2 minus 2 y minus y hat. That's my derivative at the last layer. So basically, at last layer, it's trivial to compute. And then you can compute, the previous layer, because previous layer, the layer just before the last layer depends on the last layer. So you can compute that. And then you can compute the layer before, and you can compute the layer before. So you can compute all of them to the first layer, right? So I can compute the derivative for all layers now. So you can see that, in fact, there's 2 steps. The network, actually, the information in the network go forward to compute y. But to compute the derivative, you go backward. You backpropagate this derivative until you get the derivative of the first layer or any layer, right? There are 2 passes. The derivative will be backpropagated. And the information is going to go forward to the network. Okay? And this is the base of backpropagation algorithm. So in backpropagation algorithm, you have a network, and you feed the network with one data point. But, okay, how this network is going to compute the output for this data point? You're going to assign some weights to the network just randomly. Choose some random weights. That's your initial value. And it's good to choose this arbitrary random weights close to 0. And we'll see the reason later on. So choose some weights close to 0 as random weights, arbitrary weights for the network. So you have some weights, feed the network with one data point, and then compute the output of each perceptron and the next layer and the next layer and the output. So you have some y hat in the output. So when you apply X to the network to input layer, calculate the outputs of input neurons. And then you propagate the output of each layer to the next layer until you get the output. When X reaches the output layer, so you have Y hat, then you can compute basically this quantity for the last layer. For random weights, you have Y hat. Now you can compute this quantity for the last layer. Now you can backpropagate this delta to compute the delta of the previous one, and compute the basically using this recursive formula. You can go back, and then you have delta of all layers. Delta of all layers, you have delta I, you have delta J, you have all of the deltas. Then when you have all of the deltas, it's easy to compute the derivative, because derivative was simply delta I times ZL, and you have the ZL. ZL is the output of a perceptron. And you have the delta, and you compute, you have the derivative with respect to that weight. If you have derivative, then you can apply gradient descent to that weight, the same way that we apply gradient descent to perceptron. So the new weight will be the old weight times some learning rate times the derivative with respect to UIL, which this derivative doesn't have a closed form anymore, can be computed using this back and forth algorithm, which is called backpropagation. Okay, so the search algorithm still is gradient descent, but the way that we compute the gradient is backpropagation. Okay. So that was for one data point. For this data point, I'm going to update my weights. So I started with some random weight. I feed the network with 1 point. So I will update my weights using this data point. Now feed the network with the second data point and do the same thing. And with the third point and do the same thing. And with the last point n and do the same thing. When you do one pass of all of these points, it's called one epoch. Okay? And usually you have to go through many rounds until it converges. And in practice, actually, when you go through many rounds, in each round you basically shuffle the points. You don't keep the order, from 1 to n. In the next round, you shuffle the points to avoid local minima, to avoid oscillating between some weights. Okay, that was backpropagation and gradient descent. Any question? Yes?
What is shuffling the weights?
Not weights, shuffling the points.
Yeah, how does that?
Just randomly change the order. What I mean by shuffling the points is that you have n data points, you feed the network with the first data, and then you feed it with the second data, and you feed it with the last point. Okay, that's one epoch. It hasn't converged yet. Now I'm going to do it again. So we can keep the same order, x1, x2, but my suggestion is that I don't do that. Randomly change the order. This time, feed with x2 and with xn, x5, x1, x3. And then next time, do it with x5, x10, xn, and so on. When you do different epochs, don't keep the order. Neural network comes with many heuristics, and there are many heuristics actually to get it right, to make the algorithm converge. And from time to time, I'm going to mention some of those tricks, and this is one of those tricks that going to help actually. Yes.
So, do we need to compute the weights for the other layers also?
For
So, you on the slide you updated the weights between the layer L and I. So do we need to update the weights for layer I and J as well?
yes, yes. That was just an example. That was just a snapshot of your network. You have many layers, and you have to compute it with all layers. Yes. Yes.
Is there some intuition behind this shuffling heuristic as to why it might give some advantage?
Any intuition behind
Behind the shuffling heuristic.
that why it might help? I don't know. I will think about it. Anyone has a good intuition? But yes.
Usually use it, you have batches that you form gradient descent on.
Yeah, but we are talking about gradient descent. We are not talking about batch gradient descent yet.
Right, but like when the shuffling, you'll shuffle it and then you'll create the batches and then you'll compute like grade descent separately, like on each batch, and then you'll update the weights after that, right? But the shuffling is so that the batches are randomly, like the points are randomly distributed within the batches. That's why you shuffle it. But I don't think for, like it matters because you're summing all of the gradients anyways, right, at the end. So shuffling it, if you're just performing gradient descent on the entire batch, like on the entire data set, I don't think shuffling really matters.
Help. Any other idea? Yes.
It helps to generalize the learning.
Why?
Basically, if you take one batch from x1 to xn.
You know, first, we haven't talked about batch gradient descent yet. Suppose that I'm doing just gradient descent, and in gradient descent, basically the gradient would be summation over all points. Still, you see this tip or this heuristic in some literature that they suggest that shuffle points, it helps. But if your derivative is the summation over all points, then this is a good question. Why this heuristic might help? Because mathematically, you always compute the summation over all points, even if you shuffle them. In the case of batch gradient descent, it makes more sense. But now we are talking about gradient descent on all points. Yes?
It wouldn't explain the whole thing, but it would help you avoid problems in general. Like, for example, if you just get your data and all of your class negative ones are at the start and all of your class ones are at the end, then it's going to always end with an implicit prior that favors class 1. Whereas if you shuffle that between rounds, then you won't end up with that problem.
In this case, probably it has to do something with bias variance trade-off. So both of them have to be reduced for your hypothesis to work better. So maybe shuffling will reduce the variance of your hypothesis class.
Why?
I'm just guessing because you randomly.
Yeah, I was going to say that there needs to be a clarification about whether you forward propagate all of your samples first before doing a backward propagation, or whether you do a forward propagate and backward propagate per sample. If you do the first method where you send everything through a network first and then you sum the weights and then, or sum the errors and then back propagate, shuffling doesn't matter. But for the first case, or for the second version, it would, because of the example that was given. You don't want to give preference to the first example, so it's steam. That's why shuffling matters. If you do the scheme where you forward propagate one sample, get the errors, back propagate, and then take another sample.
Right. Yeah, that's a good point.
Like, there's no way it matters shuffling. Or if you're updating it all at the end, if you're updating the weights at the end, shuffling has no effect because the summation ordering doesn't matter. But unless you're updating the weights after each, after each back prop, then order matters because the weighting is changing each time. But otherwise, it doesn't matter at all. There's no effect. Like your summation, it doesn't matter what order you're adding these different gradients to the weights, right? So it's not gonna. I don't.
Yeah. Okay. Yeah, I agree. I think, if we do vanilla gradient descent, it shouldn't matter that much. But if we have, unless we actually do basically point by point, and we don't want to give preference to, a class, for example. But maybe in batch gradient descent, it's more clear that way it might be helpful. But okay, what I told you was gradient descent. What we use in practice usually is stochastic gradient descent. And in general, suppose that you have a function which can be written as a sum of different functions. So Q is a summation of some Qi's, right? So derivative of Q would be summation of the derivatives, right, in general, not about neural network, in general. So that's basically the idea or the intuition behind a stochastic gradient descent. So if in each iteration you want to compute the gradient, and gradient is summation over all points, basically want to know the effect of cost function with respect to the weight for point I, point 1, point 2, point 3, up to point n. And you have to take the summation of all of them to take the derivative of y. Basically, it is yi minus yi hat, right? And your cost function is summation over all of them. When you have a large data set, it's going to be expensive to compute this in each iteration. In each iteration, you have to go over all of the data points and compute this. And in next iteration, you go over all of the data points and compute it. And suppose that you have a large data set, you're working with ImageNet, that there is 1 million data points in it. In each iteration, you want to have this summation. It's going to be expensive, computationally. Okay? So the solution that has been suggested actually is stochastic gradient descent. So at each point, instead of taking derivative, when you are computing the derivative, instead of computing derivative as a summation of all of this derivative, compute the derivative only for that single point, not for all of them. Okay? So it means that, that's what gradient descent is. W would be the new W would be old W minus a learning rate times the gradient of the cost function Q, and the cost function Q is summation of Qi's. But in stochastic gradient descent, we don't compute this for the summation, we just compute it for a single point. So we don't have this summation, just compute the gradient at that single point. This is called a stochastic gradient descent. Okay? So gradient descent is for all points. A stochastic gradient descent is for a single point. And between these two is, in fact, what's called mini batch gradient descent. And this is the most common one. So gradient for all of the points, a stochastic gradient for one point. Not for all, not for one, go somewhere at the middle and choose a batch of B numbers and compute the gradient with this for this B. Instead of computing the gradient for all of them, which is expensive, instead of computing the gradient for only one, which might not be that informative, compute the gradient for a subset of data, a batch of B of data, and this is called mini batch. And this is the most common one. So basically it has a scheme like this, that in each iteration, you're not computing the gradient for all of the 1 million points, but you're computing the gradient for 10 points, for example, for 20 points, a mini batch. Okay? And this B itself could be a parameter of your algorithm learning rate also is going to be a parameter of your algorithm. And as I told you, there are many heuristics for basically doing this optimization. Better moment method, and by recently I mean after 2015, there is an algorithm which is an extension of this stochastic gradient descent, which is built in all of these packages called ADAM, adaptive moment something. It's called ADAM, and so if you want to have a general rule and you're using like TensorFlow or Cross or whatever package that you're using, most of the time ADAM would be the best choice that you can have for optimization. That would be an extension of this stochastic gradient descent. We'll talk about it more in the next lecture. Any question? Okay, see you on Thursday.